Thank you very much for coming. It's a thrill to see so many people excited about the beauty of mathematics. Thank you very much for coming. It's a pleasure to introduce this evening, together with Maths Soc, Sir Michael Atiyah. I'm not going to spend a lot of time discussing all of his achievements, but you all surely know about Michael and Lily every time you walk up to the third floor of JCMB and you see their portrait gallery there, which has a lot of living history of mathematics. And so it's a pleasure and a great honour to introduce Sir Michael Atiyah, who's going to speak to us about the beauty of mathematics. Thank you.
Thank you. Well, it's unusual for a mathematician to address an audience this size, I have to say. It doesn't happen every day. The only places I remember where competition is when I once lectured in India, in Calcutta. That's not really a fair comparison. The population of Calcutta is not known exactly. It's around 20 million. You would fit the whole of Scotland into the margin of error population of Calcutta. So you've done pretty well to fill a room like this. In Calcutta they have a slightly bigger room and fill a bigger queue. Not bad there, no. So now I'm going to talk to you about beauty in mathematics. In some sense, I expect I'm preaching to the converted, because most of you here are studying mathematics because you like it or enjoy it or find it beautiful. So it's nice to have you come along and we can share this together. But I'm going to adopt a particular point of view to sort of explain what my aim is. So that's my title. Now, I'm going to start with some quotations by famous mathematicians which show an appreciation of the notion of beauty in mathematics. They all say things about beauty. So here is famous G.H. Hardy, one of the famous mathematicians in Cambridge in the early part of the 20th century. He died shortly before I went to Cambridge. He says there is no permanent place for ugly mathematics. Now, you wonder where mathematicians are very precise in their use of language. Think about it carefully. What he's really saying is that the first time a piece of mathematics is discovered or proved, it may be a bit rough, rugged, unpleasant looking, but it is important enough. People will go on polishing it and shining it up like a rough diamond. By the time they finish, it'll look really beautiful. So at first sight, it may be ugly, but if it's really important, it won't stay ugly. Second quotation is from the famous German mathematician Karl Weierstrass. There's his picture, and he was a very severe mathematician. His mathematics was very highly rigorous. He was an epitome of rigor in mathematics. Yet, here he is waxing lyrical. It is not possible to be a complete mathematician without having the soul of a poet. Now, could you imagine anything more poetic than that? He doesn't look poetical, but obviously inside, there's a hidden soul you can't see. But I mean, I think that conveys a lot of the spirit. Mathematicians really love beauty, and if you don't love it in that way, you never become a good mathematician. So mathematicians have to be poets. Now Dirac, he looked like a poet. When I knew Dirac and I came to his lectures, he was a bit older than that. By that time, he looked more like a poet. He had long, wavy hair. I saw this chap in the corridors. I thought, he can't be a mathematician. He must be a musician or an artist of production. And that was Dirac. And anyway, what he said was very succinct. Dirac was a man of very few words. He says, a physical law must possess mathematical beauty. This is his dominant theme of his life. And he did find some beautiful equations which exemplify his belief. There's a story that he went to Moscow many years ago. When he was there, he was said, please write up an equation on the board. So he wrote up the equation on the board, and he preserved it ever since. You go to Moscow, they'll still show you the equation that Dirac wrote down. Come to Hermann Weyl, the famous German mathematician who was one of my heroes, and he says, I did actually just see him once at an international conference. He gave us a speech. I heard him talk. In his work, he says, my work has always tried to unite the true with the beautiful. And when I had to choose one or the other, I always chose the beautiful. Now, some people might think he was pulling your leg, or else it was meant to be deliberately provocative. But I'll try to explain quite what he meant, and why there's some truth in this apparent paradox of mathematicians preferring beauty over truth. Now, let's start off by asking ourselves, what is beauty in mathematics? You all should know, but I often give such lectures to the general public, then I have to explain. So, presumably you're a member of the general public, and if you are, if you've walked in off the street, don't know anything about mathematics, well, here's your chance to learn. So, I want to explain what we mean by beauty in mathematics by giving some simple examples. The best way to explain is to illustrate by examples. And secondly, I want to raise the question, why is it so important? Why is beauty actually important to mathematics? These mathematicians I quoted, obviously for them it was important to say that. So why is it important? And secondly, lastly, how does it relate to truth? What is the relationship between truth and beauty? There's a famous quotation of Keats, which says they're the same. That's not true. Poetic license. Let's start off with a very famous classical result. If you all know, there are an infinite number of prime numbers. For mathematicians, I don't need to tell you what a prime number is. So you start to write them down, 2, 3, 5, 7, 11, I haven't missed any out. And then the theorem says this process does not stop. You go on indefinitely. And proof is a classic example of beautiful proof by contradiction. Is let us assume there are only finitely many primes. Let us enumerate them. Let's call the last number big P. Then multiply all the prime numbers together. 2 times 3 times 5 up to big P. And add 1. Look at what you've got. What divides it? 2 doesn't divide it. If you divide by 2, 1's left over. Divide by 3, 1's left over. All the way up to P. So none of the primes you've got divide it. So this is a number not divisible by any prime. We're assuming that every number can be factored into primes, or into prime itself. So there's a contradiction. So the theorem must be true. It's a beautiful, simple, logical example of going back a long way. This is a very old proof. But nevertheless, it encapsulates the elegance of mathematics in terms of beauty, simplicity, rigor, and succinctness. Now let's take something slightly more complicated. That was to get you warmed up. Now, here you've got to put your thinking hat on. Let's look at a bit of number theory. Let us look at sums of squares. If you look at odd numbers, if you look at prime numbers, other than 2, they're odd. But an odd number can go on to 2 kinds of odd number. When you divide by 4, you can have 1 left over, or you can have 3 left over. So they fall into 2 classes. You write them down: 5, 13, 17, 29 on one side, 3, 7, 11, 23 on the other side. And then if you play around with them, you observe a fact. The numbers on the left side, every one appears to be can be written as the sum of 2 squares. 5 is 1 squared, 2 squared, 29 is 2 squared, 5 squared. And if you find the rest of the lecture boring, you can go on trying to write all the other ones. And if you're really smart, you can give a proof by the end of the lecture. On the other side, exactly opposite. None of the numbers can be written as sum of 2 squares. Well, this is a remarkable fact. Simple, beautiful, but actually the proof is not that elementary. If you haven't seen the proof before, and you can prove it during this lecture, I'll give you a prize. I don't know what a prize is, but in case too many claim it. But anyway, this is a good example really of a simple, elegant piece of beauty in mathematics. It's very striking, and of course, this is the beginning of vast mathematics built around that example. Now let's take geometry. It isn't just number theory that's beautiful. Let's take the most famous theorem in geometry, Pythagoras' theorem. Of course, this goes back even before Pythagoras. It's over 2,000 years old, known to probably the people in Mesopotamia. And what does Pythagoras' theorem say? He says if you take a right-angled triangle, then and you square the sides, the sum of the two shorter sides adds up to the square of the longer side. That's the result. Now, how do you prove it? Well, here is the proof, which is beautifully simple and transparent. Just draw these pictures. You see, the picture is quite clear. Except this. How far these lasers really work? Oh, here we are. Okay, so there's the triangle. Has one two sides, shorter side, longer side. Now here is the square of one. Here is the square of the other one. This is the square on the opposite side. Theorem says this area equals the sum of these 2 areas. Proof Just look at the picture. Play around with it. All you've done is take these two triangles here and move them into that position on that one, that position on that one, and we rotate this one to tilt around. Lo and behold, we have one square here, whose length is this long side plus this short side. Same thing here. And so the areas of these two squares are the same, but if you remove the four triangles, here and there, you're left with this here and that there. Now there's a proof which is, I wasn't taught this proof in school, but I was taught a proof by complicated similar triangles and old-fashioned Euclidean geometry. This is much more beautiful. It's beautiful because it's transparent, it's clear. You can, once you've seen this, you can remember it. It's not that trivial. It's quite clever. If you haven't seen it before, you might have had difficulty in thinking about it. Once you've seen it, you'll forget it. That's a beautiful example of a theorem, beautiful proof. By the way, Pythagoras' theorem is not only very old, it's very important. It's still the foundation of all subsequent geometry and vast amounts of mathematics. It is the most important theorem. I got the drink from this bottle. I'm sorry, it's a bit sort of distracts me, remember? By the way, Pythagoras, although he didn't invent the theorem, his name is associated to it, and Bertrand Russell once said, he was a very provocative character, Bertrand Russell. He was a mathematician, not a philosopher. He said that Pythagoras was the most important man who ever lived. Good statement. Why did he say that? Because Pythagoras was struck by two things. First was the theorem, even though he didn't invent it. He was struck by the beauty of the theorem, and the fact that geometry could be explained in terms of numbers, squares. And secondly, he was the person who famously associated with the mathematical basis of musical tones. So mathematics is the basic of music. And this fact alone, and this geometry, made him believe that mathematics is the basis of the whole physical world. And so from that basis on, time onwards, people believed that the world outside us could be understood in rational thought, by logical reasoning. There were laws to be discovered. There was physics law, mathematics. And this was the basis of all science to follow. So all scientific theory begins with Pythagoras. So if that's true, he has a good claim to be described as the most important person. So that was Russell's quotation. Now, let's give another example from geometry. This is the icosahedron. Now, the icosahedron is not a theorem. It's an object. But an object can be beautiful by itself. It doesn't need to be a theorem. It's clearly a beautiful object. You know what it looks like. It has a nice colour size, beautiful symmetry. Now, the icosahedron is, of course, one of the other Platonic solids, but it's the most interesting one. For example, mathematically, the icosahedron is closely related to the famous theorem of mathematics. It says an equation of degree phi, a polynomial equation of degree phi, cannot be solved by roots, square roots, and cube roots, and so on. That fact, very famous result in mathematics, is closely related to the symmetries of the icosahedron. The icosahedron, by the way, is one of the few things, I mean, the other things like the cube and even the dodecahedron, you can find them in crystalline form in nature. The icosahedron you can't. So the first person to discover the icosahedron was a mathematician of genius. He actually is not that difficult. Easy to make. You've got to cut it out very accurately and so on. So whoever discovered the icosahedron was a mathematician, maybe sometime in the Stone Age. I don't know. Anyway, it's a beautiful object, and you polish it up, make a diamond out of it, sell it high price. Anyway, it's certainly an example of beauty in mathematics, which you can see doesn't need to be encapsulated in a logical form of theorem. Now, let us try and see what are the characteristics of beauty. What is it that makes things beautiful? In mathematics or in other fields. Beauty is something which applies, of course, to art, music, literature, painting. So, in mathematics, let's focus there. What is it that makes things beautiful? First of all, elegance. Things should be elegant, not unnecessarily complicated. Elegance is a criterion. Secondly, it should be clarity. If you want to have a theorem or result, it should be clear and transparent, not obvious, but it should hold together in a way that you can understand easily. Clarity. And in some sense, it should be simple, but not too simple. Something too simple is rather dull. A straight line is simple, but it's not. So what you want is some complexity, which is controlled by simplicity. It's a very subtle notion. Simple, something simple, but with complex things behind it. Like you can write a whole essay on that. Then originality and surprise. Something in mathematics which is expected, sort of routine, not really exciting, not really beautiful. Things that are really beautiful are the surprises, unexpected things. Things you wouldn't expect to find. New things. Surprise is, or originality is key aspect of beauty. Depth. Now depth is very hard to define. Deep. There's a famous quotation, I think, of physicist Pauli, who said that a deep truth is a truth whose opposite is also true. And that's a deep truth itself. Depth is a very difficult notion to define, but something that's superficial, something that's deep. And real beauty is deep, it isn't just superficial. Something you say is skin deep, but that's not on the surface. Importance. Again, beauty is you can have rather trivial forms of beauty, but you can have important things. Pythagoras' theorem is important. It's an important theorem still 2,000 years after it was discovered. And so importance is part of the attributes of beauty. All these things together are aspects of beauty, but at the end of the day, you know beauty when you see it. Like a painting. You can talk about it at the end of the earth, why the colours are beautiful, and the perspective of light, but the difference in one picture and another one, it strikes you immediately, you say that's beautiful. So beauty is something you recognise, and you recognise it in mathematics as you do in art. So there's that kind of definition of beauty. And now let me talk to another important notion in mathematics and science, which is understanding. The aim of all science, I claim, is to understand. We want to understand the world outside us, how things work. The aim is to understand. How does that work? Well, you have to organise the knowledge outside so the human mind can comprehend it. Understanding is a human activity. It's not a question of programming a computer. We want to understand the world, and it has to fit our notions of the human mind the way we think. And so we want to reduce all the complexity outside to a small number of basic principles, which quite often we formulate as laws, mathematical laws, the laws that Dirac mentioned. And we want to hold those together in some kind of harmony. And then the beauty is the thing that holds it together. Few principles held together in a way that you might call a theory, beautiful, is what makes science comprehensible. So I'd emphasize at the bottom, science is not just a data bank, it's not just a collection of facts. And the human mind is not a computer. If the human mind was like a computer, it would just think in terms of large numbers. You'd ask, you want to know what the answer to an experiment is, you might just ask, and the answer would say, this, carry out, do this, do that. But you wouldn't understand why it works. So it's not just a question of knowing the results of experiments, knowing the data, knowing the facts. It's trying to understand what lies behind them. That enables you, of course, to predict other facts. So understanding is the key to science. And if human beings didn't have this need to understand built into their brains, they wouldn't have developed the kind of science we develop now. We might have been robots. We would have developed science which is consists of just like a computer, push buttons. You know, what's the answer to this? And Google will tell you. But Google doesn't help you understand. It just gives you the answer. So understanding is a very important part of all human activity, and underlies, of course, science and mathematics. So now let me go back to the conflict of beauty versus truth, which was encapsulated in Hermann Weyer's remark that he wanted to do both, but if in doubt, choose beauty. Now, this seems really perverse, because truth in mathematics equates more or less to proof. We were told at school and so on that the most important characteristic of mathematics is you can prove something. Other fields of science, you can't prove them. You can suggest something may be true, and it might turn out to be false, and you do an experiment tomorrow. So mathematics is characteristic is that it can be proved. Proof is essentially 100% truth. So truth seems to be equal to proof in mathematics. In mathematics, by definition are told, the proof is what determines mathematics. How can we discard truth? How can we choose beauty over truth? This seems to be the conundrum. Let me try and explain what I think Hermann Weyl would have meant. And let me give you again two examples. And they're both historical examples. One is a very famous example relating Einstein and Hermann Weyl. Einstein, the greatest physicist of the 20th century, among other things, he developed the general theory of relativity, whose centenary, by the way, is next year. So next year, all the television programs, all the films, will all be about Einstein's theory of relativity. They're already being prepared. So the general theory of relativity replaced or improved on Newtonian gravity, and is a marvelous theory that explains vast areas of physics of the universe. Now, but that basically deals with gravitation, gravitational force. Shortly after Einstein did his theory in 1915, Hermann Weyl, who was a young man, got interested in it, and he wanted to extend Einstein's work to incorporate electromagnetism. The laws of electromagnetism have been worked out by James Clerk Maxwell, whose building is next door, lived in Edinburgh, and whose statue is in George Street. He wanted to incorporate Maxwell's equations together with Einstein's equations in some natural unified form. And he came up with a beautiful paper. He found the answer, he wrote the paper. His idea was, it's called gauge theory, his idea was that length scales could vary as you move around, particularly if through a magnetic field. Now, if you've gone through a magnetic field, you might find the length has changed, the gauge has changed. He called it the gauge theory. And with this as his basic assumption, he worked out mathematical formulae, and he got a marvelous, beautiful formula which he put into his paper. Well, when you write a paper, it's sent to a referee. And in this case, they chose Einstein as the referee. Einstein read the paper and wrote back and said, "This is a very beautiful paper. Unfortunately, it's false. It contradicts the basic facts of physics. We know that a proton, however it travels in the world and comes back, it always has the same mass. It doesn't change its size because it goes through a gravitational electromagnetic field. So unfortunately, although Weyl's paper is a beautiful piece of mathematics, it is not physics." Now, you would normally expect any sensible editor getting a report from a referee like Einstein would immediately turn the paper down. He would write to Professor Weyl and say, "Sorry, but the referee," might not mention the name, has pointed out that this and this. Well, the editor tried, but Weyl was very persistent. He looked back, argued and argued, and eventually, the editor, being an enlightened man, decided, well, we'll publish the paper, but we'll also publish Einstein's rebuttal as an appendix. So the paper appears, and you look it up in the reference, paper by Weyl, with an appendix by Einstein saying, more or less, this is rubbish. Not quite. Well, that's part one of the story. But part two of the story is that shortly after this event, in the 1920s, quantum mechanics appeared on the scene. Now, in quantum mechanics, besides there were things like lengths, there were things called like phases, angles. And although lengths can be measured, phases in quantum theory, you can't measure them. So difference in phase is measured, but not absolute phase. So because if you now interpret gauge theory as changing in phase rather than changing in length, to a mathematician, that's easily done. You put I in front, and then it turns left, straight line into a circle. So with a small change, an imaginary number instead of a real number, the argument of Einstein collapses, and Weyl's formulas work. Not only that, they become the basis of modern physics. The whole of modern physics since that time is called gauge theories, is based on Weyl's paper. If the referee had turned it down, that wouldn't have happened. So this is a marvelous example, you see, of the triumph of beauty over what I call apparent truths. At the time, truth seemed to say, this is not true, it's wrong. But that was only apparent because they didn't realize you put an eye in front and fiddle it. So, beauty eventually triumphs with a small twist in mathematics. So there's a good example of showing that Weyl's instinct, hold on to the paper, was correct, even though the argument against Einstein was correct. That's the first example. Second example is a more personal one, involving myself and my friend Raoul Bott, a great man who died in 2005. There's this picture. You can see what a friendly man he was. And this is based on a conference which took place exactly 50 years ago in a place called Woods Hole in America. It's a place where oceanographers go and have a marvelous time on the beach. And in the summertime, they allowed us to use it for a conference. And in that discussion, Bob and I came up with a beautiful new idea, lovely formula, we seemed to have many applications, and we were convinced it had to be true. But we thought, being scientists, we should get it checked. So we asked our friends. We asked our experts. There were a lot of experts in the conference of various things. We asked them to check an example, special case, see where they worked. The experts went away, and they said, it's wrong, your idea doesn't work. Well, we accepted that. We'd have gone away with our tail between our legs. But we refused. We were reluctant to give up such a beautiful idea. We persisted. And eventually the experts were proved wrong. So you see, the formula is established, and now it's a very, very basic formula in that part of geometry. And because the experts made a mistake, they couldn't calculate correctly or something, and we didn't believe them because we felt that our formula had to be true. And we were right. So beauty can triumph over the truth of experts, I think. Don't always believe the experts. By the way, in addition to this story, many years later, I was trying to get the details of this back 50 years ago, a long time. So I wrote to some of the other participants of the conference, asked them what they could remember. And blow me, they couldn't remember anything. I think in the case of Freudian memory, they didn't want to remember, they'd give me the wrong answer. They wouldn't admit it. So I've only got my word against theirs, but I hope you believe me. Now let's have a bit of philosophy. Why truth and beauty conflict, and why you might prefer beauty. At first glance, truth is objective, and it's called good because it's objective. Beauty is subjective, it's called bad because it's subjective. You know, you're told that personal preferences have nothing to do with science. Things are neutral, observers are independent. But on the other hand, you think about it a moment. Next line says, I know what I find beautiful. If I see a picture as beautiful, you may disagree with me. You may not think it's beautiful, but you can't tell me I can't find it beautiful. Beauty resides in me. It's in the eyes of the beholder. So beauty is subjective, it's what you feel. And now, in Roman time, the Latin quotation is what goes back that far. If your Latin is up to it, de gustibus non est disputandum. Even if it isn't up to it, you probably guess. You can't dispute taste. Taste is something personal. You can't argue against it. You may disagree. Second, on the hand, truth. I'm not sure what is true. At any given moment, what I have may be only a apparent truth, a partial truth. The truth may be hidden. It has to be checked, may change. The truth is something you can't actually grasp in your hand. Truth is something you search for. So scientists search for the truth. Truth is elusive. It's the ultimate goal. You never reach the ultimate goal. You're always on your way. On your way to your ultimate goal, you need some guidance. And I claim beauty provides that guidance. Beauty is the torch that shines the way forward, that tells you which way to go to look for the truth. So in that sense, they come together. But at any given moment, you trust your judgment, trust your intuition, will follow beauty, and that will lead you, hopefully, in the right direction. That's more or less my interpretation of Herman Weil's phrase. I hope you find convincing. And let me give a last word on this Herman Weil again. He says, I believe there is in mathematics, in contrast to the experimental disciplines, a character which is nearer to that of free creative art. Mathematics is not quite like science. It's not constrained by the physical world. It's constrained by logic and internal thought. It's more a creation of the human spirit. And he said, this is what Weil says, it's more like what an artist paints, what a musician composes. It comes from inside us. At least in part. It's more like that than like hard science. And I think I went to the bottom. Herman Weil clearly was a mathematician with the soul of a poet. And you read his writing, you'll find that exemplified very, very clearly. In one of his books, he wrote, it was the first book he wrote in English because he was German, went to America, so he wrote this book in English. At the beginning of the book, he apologizes profusely for writing, basically in a foreign language. He's not very fluent. He writes in a language not sung by the gods of my cradle. Well, that's kind of poetic term that you wouldn't think of. So he was really a natural poet. Now, in recent years, I've got interested in the neurophysiology of beauty. That means we think we're talking about things of beauty. We use the same word as artists, composers, and so on. But do we really mean the same thing? I mean, is the beauty we see in mathematics the same beauty somebody recognizes in the Beethoven Symphony? Well, how can you test that? Well, nowadays you can. The science of neurophysiology has reached the point where you can test out various things in the brain. If you ask somebody a question and they give an answer, they can, without cutting you open, which is very nice, they can do it externally, they can tell you which part of the brain is involved in your thoughts. And by doing that, they can identify the bits of the brain that think about particular things and particular beauty. You can find the part of the brain that is concerned with beauty. And that's a common part, whether it's in music or painting or literature. The question is it also the common part of mathematics? Well, my friend Sir Michael Atiyah, who is a neurophysiologist, distinguished at University College London, by the way, like me, shares a Lebanese ancestry. He and I got talking quite a long time on this. And eventually, he carried out his experiments. He got a bunch of students, and he gave them a long list of mathematical results, equations, asked them to say which was beautiful, which wasn't beautiful, put them in a scanner. It doesn't hurt you at all. You go in, you have to be safe. And then he correlates the results, and by looking at in the scanner, they see which parts of the brain are involved in the questions of beauty. They weren't trying to find out whether they were right or wrong about it, simply which parts of the brain are involved in the mental process of analysing beauty. And lo and behold, they found that you do all the right bits of correlation and careful double checks and so on. The part of the brain that is involved in recognising beauty in matter is also the same part of the brain that recognises beauty in the arts. So, it's a marvellous bit of modern science that you can test things which in the old days would have been only able to be examined by philosophers and psychologists, and they would talk about it for centuries without coming to any conclusion because you couldn't prove anything. Now you can do some proofs, and this is at the beginning. By the end of this century, young people here are just beginning to embark on, we'll know a lot more about the brain, about how the brain thinks, and we'll learn a lot more about how the brain thinks about mathematics, for example. Another question I studied with my friend Sir Michael Atiyah at the beginning was, what's the most important thing in mathematics? Fundamental notion. The question was, is the brain hardwired to do mathematics? Now, we're hardwired to survive the terrors of the jungle, natural selection, but are we hardwired to do mathematics? Why was mathematics useful to primitive man? It's not clear whether, escaping from the claws of a lion, tiger or a lion, whether knowing Pythagoras theory would help you. So, the question is, what is it most fundamental thing in mathematics? And can we look for it? What's something simple that you can look for? So I suggested to him the most fundamental notion in mathematics is not an equation, not an equality, but an inequalities. Saying this is bigger than that. And that can happen in many forms. You can have a larger volume, a heavier weight, a brighter light, a larger sound. Lots and lots of experiences can be calibrated by size. And this is the notion, the beginning of the notion of measurement, inequalities. Mathematics grows out of trying to make that more precise. So, okay, you can take a bunch of volunteers, again, the same, you lot over there, you bring them forward, and you subject them to visual, sensory experience of different kinds, and see whether you can find out whether there's a part of the brain which has because the abstract notion of size, or inequality, is the fundamental bit you need for mathematics. And lo and behold, you do find a bit of the brain that actually does work on inequalities. We didn't publish that paper, unfortunately. The Frenchman got in first, And that's tough. And life was in the science is like that. We just were about to publish it, and the Frenchman beat us to it, so we had to do something else. So we moved on to this one, which is, I think, also very interesting. Now, this paper was published in February of this year. It went onto the web, and within a few weeks, I don't know about this thing, but he tells me there were 80,000 hits. It went around all around the world. Articles appeared in the New York Times, the London Times, Scotsman. Everywhere you went, you could read about this result of this experiment. So, it was fame, and a bigger audience than this, thousands of people. And if you're interested, you might like to watch out. Next year, Samir and I are going to organise a conference here in Edinburgh, the Royal Society of Edinburgh, on the science of beauty. And we'll bring together 2 days lecturers on all sorts of aspects, the beauty from the arts, sciences, neurophysiology, all that, to exchange ideas about beauty and the way it interacts with science. And you'll get more details if you watch the web, and you're welcome to come along. It'll be an open meeting, hopefully. I'm not sure we've got a room big enough as theirs, but we might have one of the shifts in location. Anyway, I think I've finished my time. I did say that I'd stay around for a while and answer questions. Don't make too difficult questions. And the questions don't need to be only on the lecture. You can ask me easy questions like what's 2 + 2 as well. So I think I'll hand back to the chairman, and somebody else will do the organising of the next questions. Thank you.
Firstly, I'd just like to say thank you very much to Sir Michael Atiyah for that really incredible talk. It was just really inspiring and amazing to hear. And I think I'm going to be a little bit selfish right now and might take the first question for myself because I feel like I'd be kicking myself if I didn't ask. You've talked about beauty mathematics throughout, and I was just wondering what piece of mathematics is your personal favourite? Unless that is too hard a question.
It is hard question. No, what is your favourite piece of music? You know, it depends on your mood. All this beautiful. And one day you might prefer Beethoven, the other day you might prefer Bach. And you can't linearly order them. Same as with mathematics. Mathematics has a wide range of things, depending how you feel. Are you feeling tough? You want to make important. When you want something elegant and beautiful, you want something to help you go to sleep. So same thing as I mean, if I ask you what's your favourite piece of music, do you have a favourite piece? It's a rather naive question. So I don't think. It's a good question, but the answer is too complicated.
What advice would you give to a young mathematician?
What advice would I give to a young mathematician? If you enjoy mathematics, keep at it. You have to be persistent, because there are times when you struggle and things don't go right, and you feel like giving up. No, you have to persist to get through that. And eventually there is light at the end of the tunnel, the famous phrase. When I was a second-year graduate student, things didn't work very well. I thought of giving it up. I started going to lectures on archaeology and architecture, all those other things. And you know, it's touch and go whether I would carry on or not. Then, if you wait long enough, you'll get, so you can hold on. There will be difficult times. You don't get there by the easy route, unless you're a genius. And I was told the same story by a very famous mathematician, Jean-Pierre Serre, probably the most famous mathematician of my time. He said the same thing. Half or part of the way through his research, he almost gave up mathematics because he wasn't. The reason is, if you're as good as him, you realise only worth doing really important things. And if you can't get a really important result, you give up. If you're not that good, you don't realise it's not important, so you can be satisfied with lesser results. So, anyway, persistence and enjoy it, because mathematics is a beautiful subject. If you don't enjoy it, you better do something else.
You gave some rather beautiful examples of beauty triumphing over truth. What would be a good example of truth triumphing over beauty, if there is one?
Well, my whole point was that that's the wrong question. You shouldn't have no, that's not quite true. I mean, many good ideas in mathematics we put forward, for example, in relation to physics, and it turned out not to be right. For example, the very first ideas about what atoms were put forward by people in here in Edinburgh, Glasgow. Kelvin thought that atoms were really not in vortices of ether. Yeah? Knots were the answer to what atoms were. And people worked hard showing all the classification of knots. If they'd been right, instead of having a periodic table in every chemistry lab, you'd have a picture of knots. Well, it turned out to be wrong. That wasn't the theory, but because beautiful result lives to fight another day. And 70 years later, the topology involved in things like knots has reappeared in physics at a much more fundamental level. So a good idea, it may be the wrong attempt for that particular question, but it may survive. So it's a running battle. You lose one battle and you win the next one. So I like the example. If you go and pick flowers, you shouldn't pick flowers really, but if you you may want to put some flowers in the vase. You come back and you find they don't look very good in that vase. You hunt around and you find a better vase and they look beautiful. So it's a bit like that. But mathematics may not solve the first problem if you try physics, but if it's a good bit of mathematics, it will solve some problem.
Hi, what I'm interested is that as you said a lot about beauty, and my first part of the question is how you use the beauty to inspire you, as well as testing among the truths and other research, like previous results in the meanwhile. And also, according to your long-time research, if to be concrete, like in geometry, according to your feeling of beauty, do you have some particular idea which you might expect which will happen in the future, which will change our mind and give some very beautiful results? Thank you.
Well, to summarize, I think the first question was, how does beauty affect your work? And I think the point is that the feeling, the search for beauty, it helps you to sift out all the possible things in front of you, the most attractive ones, and you hold on to that. Gradually you build up a beautiful structure. So beauty is the thing that guides you as you work your way with the tools that you've got. As far as predicting the future, geometry, what beautiful results might we get for the future of geometry? Well, it's always safe to predict things, what will happen in 50 years' time, because I won't be around in 50 years' time, some of you maybe. So Einstein thought that geometry was the fundamental way to explain the physics of the universe. He succeeded with gravitation. When Clerk Maxwell came along, he succeeded with electromagnetism. Sorry, Boyle came along, he succeeded with Maxwell's equation, electromagnetism. But we have many more complications in physics. And the question is, can you solve all of these by geometry? Einstein's dream. People thought Einstein was crazy, but maybe in 50 years' time, we'll find he wasn't so crazy. That's the kind of thing I like to think about.
Yeah, so I mean, sort of the common theme sort of throughout the entire talk, and also to your answers to previous questions, has been sort of that mathematicians are often driven by beauty, and if nothing else, while doing maths, even if you're struggling, you should at least try to enjoy and appreciate it for the beauty present. I want to go back to sort of actually something with that in mind, I want to go back to what you said when you were talking about Pythagoras' theorem. You showed us a very simple and elegant proof, but you also sort of said in passing that when you were in school, that's definitely not how you were taught it. You sort of shown some rigorous Euclidean geometry, blah blah blah. I think that actually brings home with quite a lot of people. In school, you're often not taught maths through elegant geometry. You're not sort of presented it as something which is beautiful. You're presented it as learn this or you won't be able to function in the adult world. And I think quite a lot of people, are actually put off maths at a young age because of that approach to teaching it. Would you say that it would be a lot easier to inspire more people to enjoy and study mathematics if there were a lot more emphasis on presenting mathematics as a subject of beauty?
Yeah, I think you're right. I mean, certainly, the whole question of education is a very complicated story. But no doubt about it, you can only succeed if you interest the children you're around to teach. And you have to go out and what these people attract them. Now, playing with shapes, examples of Pythagoras' theorem, we cut out, is playing with shapes at the same time as doing some mathematics. So I think playing with shapes in all sorts of sizes, circles, triangles, squares, building blocks, that's very good. I mean, it's on one hand interesting, children enjoy doing it from any age, and yet it's building part of the process of learning mathematics. So I think more attention to that aspect of mathematics and teaching would be a good idea. Of course, you still do the formal parts alongside, but it should be balanced, and you should enjoy the parts that involve putting things together and playing around. And whenever you can really do something serious with it, you should. People quite often think that just drawing pictures and so on is not rigorous mathematics. You have to write in a formula. That's wrong. A good picture is worth its weight in gold, and you can convert that into algebra if you like, but that's just like changing dollars for pounds. Not the way around which it is, but I think you're right that trying to educate people, you must interest them and elementary geometrical configurations are a very good way to start.
You've probably been asked this several times, okay? So, what would you say, in your opinion, is the most beautiful equation in mathematics? Did you ask that? No.
It isn't quite hard. Anyway, the answer to that question is, we've been through that many times. Everybody knows the most beautiful equation in mathematics is e to the pi I equals -1. I like to, because it has within it all the first important numbers, things in mathematics, e and pi and I. So, in one beautiful, very deep result, not trivial. And I like to tell the general public, this is mathematics. When a phrase like to be or not to be is in Shakespeare, because that is a very short, it uses just small letters, small words, yet it has a very deep meaning. So that's the kind of analogue I like to make. To be or not to be, e to pi r.
You talked about, one of the most important things a mathematician needs to have is persistence. Like when things got really bad in your career, or the really low points, and you considered giving up, who or what sort of inspired you to keep on, to persist?
Well, very hard to know because it's a long time ago. You can work it out. I think, to be quite frank, what happens is I won a prize. You always wonder whether giving prizes is any value. But if you get a prize at the right stage when you're really low, it raises your morale, and that can do wonders for you. So, I was very pleased that I got that prize. It made psychologically a big difference. At the moment when you need encouragement, I could have come from other sources, but and of course maybe other things at the same time. You solve a problem, you make progress, but getting through the difficult bits is tough. You need support from your friends, your girlfriends, your parents, your colleagues. You need psychological support. You go and weep on somebody's shoulder and say, "Oh, my equation doesn't work today." If you can't have a beer with me, relax a bit, enjoy life, and then next day you'll feel a bit better.
So you mentioned the genesis of fundamental results in mathematics. At the beginning, things are maybe ugly, and then people polish the results and the presentation of it. There's actually a downside of being fed only the polished, perfect-looking results when we learn mathematics, because when we want to try to do research, we're inhibited with the idea that it has to be beautiful, clean from the beginning. And my advisor told me that it's a bad thing that we learn these things in such a slick presentation that we think it has to look the same. But actually, when we try to do mathematics, we have to be rebellious. We have to just do things that are just awful. We have to, we have to allow ourselves to say, okay, I'm not going to show this to anybody else, but I'm going to have to go through this piece of junk because I have to break through something. So I think the two have to be, we have to carry both.
And I agree with you, and that's partly why I said it. The first steps in mathematics are quite often cumbersome and so on, and then they get polished up. And then, if you then learn them, the other side, in a book or through a lecture, you only learn the polished version, you haven't been through the same process of struggle. You don't learn something unless you struggle. If you get the answer very easily, the next day you'll have forgotten how you got there. So you must learn to struggle, and so people should hold back to let you do the work yourself. You learn by doing. It applies to everything. And when you do it yourself, you're not that smart, but you get the best approach every time. So you're quite right. Learning, and that applies to all books. Most mathematicians, when they write books or papers, don't present the way they discovered them. They don't say, I spent 6 months struggling on this question. I couldn't do this, I couldn't do this. Eventually I got, they don't go through that whole train of thought, which was essential for them to get to the answer. They say, consider X, prove 0. That's not the way they worked. They present the answer as though it was. That's misleading. And of course, you don't want to overdo it. You don't want to pour every student to go through this, all the painful works that everybody else has done. We never make progress. You want to balance it. But you must show that you have to make mistakes, you must struggle. One of the reasons is that you must, to appreciate the subtlety of the beauty of something, you must learn all the things where it wouldn't work. Why the people did it this way? Why was this particular definition chosen? And you don't do that by just learning the definition. You have to try and find your own versions and find what doesn't work. And struggling through that, you eventually get to something good. So you're quite right. I wasn't disputing that, but hardly wasn't disputing it either. It's part of the learning process. Not always. You may have a beautiful idea. Dirac had a beautiful. He thought, "I want a beautiful equation," and he wrote it down. Sometimes it happens. God, gives you inspiration. But a lot of the time, as they say, genius is 99% perspiration and 1% inspiration.
You said, at least from an evolutionary point of view, that you thought inequalities were sort of the fundamental, earliest sort of mathematics we did. I would say that you're not really doing mathematics when you're just using inequalities, at least in some basic way. You're only really doing mathematics when you make an abstract step. So you say, understand that comparing the size of a cow with a smaller cow is the same sort of operation as comparing the size of a dog with a larger dog or a smaller dog. So I wonder if you've given any thoughts.
Well, no, you didn't quite catch my point about this experiment which I talked about. I mean, knowing the abstract notion of inequality, which is mathematics, says that differences in size, whether they're cats, dogs, or volumes or sound or light, this is an abstraction. And the question is, does the brain have within it that built-in notion of an abstraction? And that's what I was going to ask. That's what we found. The brain does have essentially part of the brain that's concerned with inequalities in any shape or form.
So
it is the abstract notion, and that's not big in mathematics. You're quite right.
But did you look at the newer correlates of abstraction rather than of inequalities?
We're just making inequalities in different media. An inequality which concerns itself with volume or sound or light or shape, this is an abstraction. We're doing the same things. That is like abstracting a number. Apples and oranges are things that you call them objects, and then they become all under one heading. So mathematics starts with abstraction, and abstracting inequality is, I claim, a very early start. That's what we're testing in the physiology experiment, and we found that there was a part of the brain that did abstract. It didn't have one part of the brain that measured differences in size of volume, another light. No, the one part was common to all. So it definitely dealt with the abstraction.
Okay, I think I can kind of feel the vibe of what the answer of my question is going to be.
Why ask?
Well, personal confirmation, I guess. Well, I'd like to know what your opinion on deadlines is, and like how on deadlines.
Deadlines.
How deadlines have influenced your working career and like your creativity in general.
Deadlines. Well, I think we've got to get out of the building by 6 o'clock. That's a deadline. We're a bit lax. I mean, when you take an examination, you have a deadline. You 3-hour paper, you think, but of course you have to work to a deadline. But in normal mathematical thinking, there are no deadlines. It's open-ended. You may make a temporary deadline. You say, I'd like to solve this theorem, before I die. That's literally a deadline. But other than that, you're open-ended, and you can set yourself temporary deadlines. Now, a deadline is not an important part of the process. It's the reverse. It's an obstacle. You shouldn't have artificial deadlines. You should let the thought process flow, and it flows at its own pace, slow, fast. How lucky you are, right? But the deadline is no help. Not quite true. if you've got to do something about it next week, it does help to organise your life so that you finish. Practical level, but in terms of serious mathematical thinking, it doesn't help. Didn't help Newton say, well, I've got to solve the law of gravity, by 25th of December. It didn't happen, or we'll make apple falls.
So, I'd like to present this card. It's from the Maths Subcommittee and a few students about it who've put a lot of time and effort into sorting out some of the party, and we'd just like to present this to you, Sir Michael Atiyah.
Thank you very much. It's interesting to see, wow, how many famous names appear out of this in 50 years' time.
So there's a reception back in JCMB in front of the Atiyah Portrait Gallery. And so Michael will be coming along as well. I'm happy to talk to anyone who has some other questions and so on. So thank you very much for coming.